Well, here we go, continuing on with fluid dynamics and our discussion on Bernoulli's principle. In this video, we're going to look at Bernoulli's equation and learn how to apply it in situations of fluids in motion. As I'm sure you recall, Bernoulli's principle simply states that when the speed of a fluid increases, its internal pressure decreases. So the slower moving fluid in a wide section of pipe has a higher pressure. The faster moving fluid in a narrow section of pipe has a lower pressure. Now, Bernoulli's principle is really just a consequence of the conservation of energy. Bernoulli himself developed an equation which relates pressure and velocity in a fluid system, which we call Bernoulli's equation. Here we start with the pressure. We have here an expression for the potential energy within that pipe and an expression for kinetic energy within that pipe. Now, the conservation of energy states that the total energy of an isolated system has to remain constant. The fluid flowing through a pipe is an isolated system, so the total energy at one point in the pipe must equal the total energy at another point in the pipe. Now, in this equation, P here, that's the pressure in the fluid, the internal pressure. Rho is the fluid density. Y is the height of the fluid. And this V is the fluid velocity. So let's take a look at two locations in a pipe system. So Bernoulli's equation tells us that the sum of the pressure, the kinetic energy, and potential energy have to be constant. That is, they have to equal the same thing. So we can rewrite Bernoulli's principle in this way, where we've got the energy at one side at one point in that pipe. We got the energy at another point in that pipe. If that pipe height doesn't change at all, right, we can just totally cancel out that potential energy part of it. Or if it, say, moves along and moves up onto a platform, something like this here, then we would be able to count the potential energy down at the bottom as 0, and we could include it at the top up there. So really, I mean, you got to get it into your head that Bernoulli's principle is just an expression of the conservation of energy. And these are just now more expressions for different types of potential energy. It's fluid potential energy and fluid kinetic energy. So let's take a look at an example of the pressure in an irrigation system. An irrigation system is simply a system of irrigation, like in a farm or in a greenhouse or something. So water flows through the pipes shown in this figure. The water speed through the lower pipe is 5 meters per second, and a pressure gauge reads 75 kPa, kilopascals. We want to know the reading on the pressure gauge in the upper pipe. We see from this pipe that as it's moving at 5 meters per second here, it has a diameter of 6 centimeters here and constricts to 4 centimeters here and rises up 2 meters. Now, in order to fully answer this problem, one thing is very important for us to understand. The pressure that's indicated in this problem is what's called gauge pressure. That is, it's the pressure in excess of atmospheric pressure. We have to remember, atmospheric pressure is on us at all times. In order for Bernoulli's equation to work correctly, we need the absolute pressure, which is the gauge pressure plus the atmospheric pressure. So we have to convert this gauge pressure to pascals out of kilopascals, move the decimal 3 places to the right, and then add 101,300 pascals. We always want to be in absolute pressure when we do these problems. The first thing that we want to do here is find the velocity at point 2. Now, because the volume rate of flow has to be the same regardless of what happens to the pipe between points 1 and point 2, then we can use the continuity equation to find the velocity at point 2. So we have the cross-sectional area at point 1 times the velocity at point 1 has got to be equal to the cross-sectional area at point 2 times the velocity at point 2. So the equation becomes this. We have to remember to convert any centimeters into meters, and then we can substitute in our values and solve, and we end up with a velocity of 11.25 meters per second here at point 2. We should expect an increase in velocity at that point because we have our pipe constricted at that point. So then the second thing to do is going to be to find the pressure at point 2. If we look at point 1, right, there is no, this is our 0 point for our gravitational potential energy here. So this term for gravitational potential energy at point 1 is going to cancel out, leaving us with this here, okay? Now, one thing to make sure you're diligent about is indicating pressure and density pretty, so it's obvious that you're showing density here and pressure here. So this is a rho, this is a P. All right. Now we can substitute in our values and solve. Now, when we do that, you have to remember what we talked about right as we began this problem about the gauge pressure and absolute pressure. We have to take the gauge pressure we're given at point 1, convert it to pascals, and add in the atmospheric pressure. And that'll give us our absolute pressure, and we'll get absolute pressure at the end. And that absolute pressure, once we run through the numbers, is this 105,918.75 pascals. We want this in gauge pressure, so we have to subtract out that 101,300 atmospheric pressure to give us 4618.75 pascals, or 4.62 kPa. Now, we should totally expect this decrease in pressure as we go into that constriction, right? Because the speed of the fluid is going to drop, and as the speed of the fluid drops, the pressure drops as well. So there's a whole bunch of applications of Bernoulli's principle that we can take a look at, right? Bernoulli's principle is often used to explain why birds and airplanes can fly. One of the reasons is they have these what's called a cambered wing. It's shaped kind of like an elongated teardrop. And as a plane moves, it forces air over the top of that wing to move faster than the air that goes underneath that wing. Well, because the air over the top is moving faster, there's less pressure. Therefore, there's greater pressure on the bottom, and we get lift. Your reading packet goes into a really great detail of each of these little things that I'm going to bring up, as well as a few others that you should totally pay attention to. Okay, vacuum cleaners. Okay, they use Bernoulli's principle. The way a vacuum cleaner works is you got a fan back here, exhausts air out this way, so we have moving air through the whole tube, right? That moving air is moving faster than the air outside of it, so there's less pressure in, the greater pressure out. The air pressure from outside the vacuum cleaner basically pushes dirt and dust up through the hose, okay? So there's really no such thing as sucking, okay? It only pushes. The air pressure from outside pushes through the vacuum cleaner. Mattresses, if you ever see anybody doing something like this down the road, you got to get out from behind them right away because they don't understand Bernoulli's principle of what's happening here. See, as they're moving along, the air is moving over the top of their mattress faster than the air underneath it. That air underneath it has greater pressure, less pressure on top. Pushes that mattress up. If they don't have this secured on there very well, that thing's going to be flying up into your face back here in your car. This fella should have totally paid more attention in a physics class, right? Chimneys. Chimneys work because of Bernoulli's principle, right? So a lot of homes today have a gas fireplaces, but if you have a wood fireplace in your home, Bernoulli's principle is what makes that smoke go up that chimney. You see, as there's moving air over the top of the chimney up here, that's less moving air in the bottom, inside the house there. So you got low pressure over the top of the chimney, you got high pressure here. That high pressure pushes that smoke up that chimney, right? Instead of allowing it to come float around inside your house. Bernoulli's principle is so easy to understand, even the prairie dogs understand Bernoulli's principle. You see, when these fellows go and make their tunnels, right, they always put one tunnel up a little bit higher than the other. The smaller, slightly curved hill gives low pressure. The taller, sharply curved hill gives an even lower pressure. And the pressure difference then, as that air moves over the top of the tunnels, right, that pressure difference allows the air to be pushed through the tunnel, giving these guys a nice little air conditioning system. A lot of damage in hurricanes and tornadoes and things are because of Bernoulli's principle. See, if you got yourself a house in an area where there's high wind, that wind goes over the top of your house much faster than the air inside the house, right? That air inside the house then has greater pressure than the air outside the house, and you get your roof to completely lift off of there and go flying away. Baseball pitchers and tennis players also make use of Bernoulli's principle. The curveball in baseball, it's a pitch that actually does curve. When the ball's released, it's given a spin. As it travels through the air, one side of the ball is going in the same direction as the air, so the ball's spin adds to the air velocity. On the other side of the ball, the spin is in the opposite direction of the air motion. So the air is traveling slower on that side of the ball. The pressure is lower on the side with the highest air speed. So the ball is pushed to that side by air pressure, making the ball curve. Tennis players learn the same technique of giving the ball a spin when they serve. This causes the ball to curve in the same way that a curveball curves, making it harder to return. One way companies can save money, right, is by creating buildings with ventilation systems that use Bernoulli's principle. Here we've got a ventilation system where we've got a large open area here, a small open area there. We basically got ourselves a constriction here, right, which allows the air that flows through to move faster, right? So we've got a pressure gradient, so we're going to get airflow, we're going to get a cooling system. And like I said, in your reading packet, there's several other things in there, applications that you can take a look at. It goes into detail, and we're going to look in class at some very entertaining little demonstrations of Bernoulli's principle. We'll see you then.